I welcome you to a lecture that I would have loved to give this summer in San Diego, meeting with you and sharing exciting science. I would like to thank the organizer for all the efforts they have done and for giving me here the opportunity to interact with you. I would also like to thank my colleagues at TUM and at PNNL for the excellent collaboration, the enthusiasm, and the camaraderie that enabled us to present here catalysis at liquid-solid interfaces. Now, one may ask why we should be interested in understanding catalysis in this liquid phase. We have been traditionally dealt with catalysis at more elevated temperatures and under conditions where we could practice at these higher temperatures catalysis at a gas-solid interface. And this has been the tradition for decades. As we are moving into a cyclic economy, and we would like to change not only the feedstock, but also the source of energy to renewables, we're facing a situation where we have to deal with much more dissipated energy. And therefore, if we would like to store this energy in chemical bonds in processes that are much smaller than the processes that we have been used to in a refinery or integrated large chemical plants. Now, when we think about catalysis, we normally think about pathways that we devise with new catalysts that help us to achieve a catalytic chemistry through specific interaction with that catalyst, and that enables us to come through a transition state that is much lower in energy than the transition state that would be achievable in a simple gas phase reaction. Now, we have two possibilities to actually improve that further. In one case, we can take the environment to stabilize the transition state, usually by sterically adjusting the environment to the size of this transition state and lowering by this the size and the magnitude of the standard free energy that we have to pass. There is a second pathway where we can primarily use the influence of solvents and the influence of charge proximity in order to change the ground state of a molecule that is being transformed, and also in this way lowering the barrier that we can achieve. I would like to do this and explain these possibilities using three examples. One example is the chemistry of Bronsted acid sites that are being transformed to hydronium ions, and which influence in turn the thermodynamic state of the interacting molecules. So they are changing their nature, and they change the nature and state of the reacting molecules. The second one is that when we put metal catalysts into water or other protic solvents, they may undergo electrochemical reactions, changing the surface properties and opening in this ways new reaction pathways. And the third one is that if we add an electric potential, it will then shift again not only the chemical state of the metal, but we add also further excess potentials that change the rates of reactions. Let us start with the case of zeolites and water. And I've chosen zeolites as a typical example of an oxide that we understand well. And as you will see, that enables us to more rigorously set the boundary conditions. In a naive way, one would think that if we add water to a zeolite and we add sufficient pressure, we slowly keep filling the pores until we have a homogeneous water-like environment. I will show you that this is not the case, and that this is a distinct stop at one point, and that is very tricky and difficult to fill pores with water completely. We do this by taking a zeolite. In this particular case, I have chosen ZSM5 with pores of approximately 0.55 to 0.6 nanometers. And in these pores, you do have some sites in which a silicon tetrahedra has been replaced by an aluminum tetrahedra, which generates an acid site. And we will be discussing about the concentration of these acid sites and the effect that water has on them. So if we look at the absorption of water as a function of the concentration of acid sites, you see that the amount of water that you can absorb in a zeolite increases commensurate with the concentration of Bronsted acid sites of these OH groups that we have in the zeolite. So if we take this together and normalize the adsorbed amount to the concentration of these Bronsted acid sites, we can now plot water per Bronsted acid site. We see that all adsorption isotherms fall onto 1. And that means that the adsorption is localized and the adsorption is confined to the direct vicinity of these hydronium ions. We also see that this stops around 7 to 8 water molecules and seems to be limiting before the overall water environment begins to condense. Now, let us look into more details to the heat of adsorption of water and the interaction of water with these Bronsted acid sites. We see that water at low concentrations, up to 1 water molecule per Bronsted acid site, has a much lower heat of adsorption than when a second molecule joins. So it is almost a discrete jump. And we see that this discrete jump then slowly decays, and the energy decays to the level of condensation, of the heat of condensation. And once you have reached the heat of condensation, adsorption stops, because it's entropically better to condense at the outside of the zeolite than in the confines of a zeolite pore. You may ask, why is it not starting at the higher level and then go down? And you see that the reason for this is that you pay an entropy penalty when you bind 2 water molecules and have the proton transferred. Theory shows this very accurately. You see that a single water molecule is not being protonated, and that the water molecule, 2 water molecules, then begin to have the proton transferred and share it with that oxygen. And then once you have 3 and 4 water molecules, it's really a distinct cluster that is formed. Now, if you go to higher pressures, this is a self-limiting process. And this self-limiting process defines the hydrophobicity or hydrophilicity of a particular zeolite. So there remains an empty space in. Now, if we go to a different size of a material, in this particular case, it's beta, and this has approximately a somewhat over 6 nanometer diameter, which is a large difference. You will see that we see a very similar change in energy. We see also the self-limitation, but in this at this time, this self-limitation stops at 10 water molecules and not at 8, as in the case of MFI. So we have 2 cases where we see that the pore size influences the size of these clusters, but in principle, the chemistry remains the same. So what are we doing? We're having a situation where we have a hydrated hydronium ion, and that hydrated hydronium ion is spaced by some distance from each other. And in this distance, you can adsorb molecules. It's very difficult to disengage these water clusters, but it's straightforward to have organic molecules being placed inside. Now let us try to understand what these molecules would experience when they are being adsorbed. The first part is we need to understand how a molecule at all adsorbs when you shift from a gas solid interaction to a gas liquid interface and a liquid solid interface in turn. We see that from the gas phase, the heat of adsorption is about 88 kilojoules per mole. And while in aqueous phase, that enthalpy drops to 22 kilojoules per mole. Commensurately, the entropy is negative by 186 joule per mole in Kelvin and increases to minus 25 joule per mole in Kelvin. So overall, that interaction is much weaker. So how shall we understand this? We know this is the amount of heat that we are setting free when we adsorb from the gas phase. We know this is the heat that we are setting free when we adsorb from the liquid phase. If we consider the heat of this solution of, in this case, cyclohexanol in water, then we see that the two add up. That means the only reason why this is so much lower is that the starting point is a lot lower than the starting point from the gas phase. So in principle, it's an additive behavior. Note that we have done this under conditions where there were not much impact of the environment on this molecule. And we had done it under limiting conditions that we did not have to consider any other secondary effects. Now let us see how the differences in Brønsted acid site concentrations affects the adsorption of an organic molecule. And again, I'm turning here to cyclohexanol, and we are looking here to a series of zeolites that increase in the concentration of hydronium ions in the pores, ranging from 0.6 micromole or millimole per gram to 1.15 millimole per gram. And you see clearly that the amount of organic that we can bring in there has decreased dramatically. We can compare this with two different zeolites, and we see clearly that the residual micropore volume and the amount of water per Brønsted acid sites under these conditions are 10 for beta and about 8 for MFI. So we have very predictable environments, and I can give you other zeolites, but that would go too far in this for this lecture. What happens to these molecules when they are adsorbed? We have seen that already not only the amount but the slope at which the isotherms had initially were flatter with higher concentrations of Brønsted acid sites. And this translates obviously to an increase in the standard chemical potential of the adsorbed molecule when you go to higher densities of hydronium ions, going from 110 silicon to aluminum ratio with a low concentration to 15 with a relatively high concentration. What is the consequence of this? The consequence is that the adsorption equilibrium constant changes as the function of the hydronium ion concentration, here plotted as the ionic strengths of in the zeolite, giving the density of hydronium ions in the volumes of the pores that we have. And we see that MFI and beta almost go down in parallel, but they have an offset because of the differences in bonding. And if we would look to the adsorption on a Foggia site with a larger pore, it would be down there approximately at where I'm pointing with the laser pointer on the slide. How to understand this? We have a zeolite crystal, and this zeolite crystal has pairs of hydronium ions and negative charges on the lattice. So it acts in a way like a salt solution. And in this salt solution, we adsorb a molecule with a particular standard chemical potential. And that is the standard chemical potential when the ionic strength approaches zeros, and we do not have any hydronium ions in there, plus an RT ln of an activity coefficient, and this activity coefficient is the product, the log of this activity coefficient is the product of a constant times the ionic strength. So we see that that excess potential is directly related to the log of the ionic strength. Now, if we want to understand now how this space really depends on those interactions. And therefore, what we have done in the little model, we have taken the center of such a hydronium ion and put it into the middle between two of those hydronium ion clusters. And you see that the chemical potential drops quite dramatically over a relatively short distance from the physical boundary at around 0.5 nanometer down to almost a very low value and almost the equilibrium value when you are in a distance of about one nanometer. So this is a short distance effect. This is something where we have to work with the proximity. And I will come back to this through the lecture again and again, that I will show you that the proximity of hydronium ions to a particular reaction have a profound impact. Now let us first understand what localized hydronium ions do in catalysis. So we combine the impact of that environment, because we are still in that zeolite pore, with the impact that molecule sees on its reactivity when it's adsorbed between the two hydrated hydronium ions. Let us, in the first step, look at the standard free energy along the reaction trajectory. We start with a simple association. We protonate this in the second step. The third step is we are cleaving the carbon-oxygen bond, forming a carbenium ion. And in the last step, that carbenium ion donates a proton back to the water cluster and finally forms the olefin. We analyze kinetics and show that we do have a very high primary kinetic effect. And that high primary kinetic effect means that the cleavage of a carbon-hydrogen bond must be involved in the rate determining step. And that means that the last step that we are having, the donation of the proton back to the water cluster, is involved in the rate determining step. We also see that we do have a significant oxygen exchange between alcohol and water, and that teaches us that we do indeed have an E1 type mechanism, so that we are breaking and reforming the OH group. And we do have a substantial entropy gain. This is very different from the gas phase measurements, because in the absence of water, the bond of the proton to the zeolite is much more stable. And this higher stability drags down the last step and makes the cleavage of the carbon-oxygen bond be the rate determining step. And therefore, it shows a much lower primary kinetic isotope effect. Now, we want to understand what this higher ionic strength in the ground state how this higher ionic strength in the ground state impacts the overall catalysis. We do so by first turning to a dry situation. So we want to establish that the materials that we are looking at are indeed have constant acid sites. And indeed, we've done this for two reactions. We've done this for the dehydration of one propanol to either the ether or the olefin. And you see across the concentration of Bronsted acid sites, the rate normalized to the concentration of Bronsted acid sites is constant. So the turnover frequency is constant. The same holds for the lower rate in alkane cracking. Also there is over a quite large number of molecules, the rate independent the rate is independent of the concentration of Bronsted acid sites. What happens if the same reaction takes place in water? We see that the normalized rate first increases up to a certain point and then decreases. This first increase is clearly related with the increase of the standard chemical potential of that molecule. But what's the decrease? On the one side, this decrease is related to an inability of more reactant molecules to be absorbed in the pores as the hydronium ion concentration increases. But the size of it, we will also show at the later slide that it is about the symmetry, it's about a minimum in the distance between two hydronium ions that is optimum for such a reaction rate. Can it be extrapolated? Well, if you compare now the maximum that we saw within the confines of a zeolite with the increase in the ionic strength that is in an aqueous solution of HCl in this particular case. Here, we did not change the concentration of HCl. We just added lithium chloride as an electrolyte in order to increase the ionic strength. And you see, you increase by about an order of magnitude. Look at the difference in scales between those two cases. So we do have a turnover frequency by the zeolite, which is 2 orders of magnitude, 1 order of magnitude larger than the changes that we observe in liquid phase. So overall, we know that about 1 order of magnitude is caused by the local environment, the stabilization of the transition state. 1 order of magnitude is caused by the increase of the charge density between those two hydronium ion clusters. We can do this, and we can explain this in terms of transition free energies. And you see that the chemical potential, the chemical standard potential, is a homogeneous function. So it increases as the charge density increases. The transition state free energy actually, and the chemical excess potential, those go to a minimum. And that minimum is there exactly there at the maximum. And that maximum is about the size of the volume, a symmetric volume between two hydronium ion clusters. What can we do with this? We can use it to predict catalytic activity. You see here one example. Again, the case of alcohol dehydration, where we are plotting on one of the axes the standard chemical potential of the adsorbed state, and on the other axis the standard chemical potential of the transition state, and on the z-axis here the log of the turnover frequency. And you note that for each of the materials such a maximum exists. This is for MFI. This is the maximum for beta. We haven't done this for phosphate in this point. But that there is also for a given silicon to aluminum ratio, there is a trend that is again moving to a lower activity as the space around the active site and the hydronium ion changes and gets smaller. You can use it to predict where you would expect the maximum activity and how high a particular maximum activity could be. We could go one more step. We could take the transition enthalpy and the transition entropy for all types of alcohol elimination reactions. And we can plot those against the log of the turnover frequency normalized to the active sites. And you see that all the data, all reacting molecules are on one plane. This is one plane which holds all different catalysts, independent whether this is a zeolite or whether this is a homogeneous acid or whether this is a solid, or whether this is a solid, other solid catalyst. We see that we go from low activity in E2 type eliminations in primary alcohols to very high high activities in E1 type of eliminations. And we see that a lot of this higher part is also given by a higher entropic situation, a higher entropy, a higher transition entropy. So having such a plane allows you now to take an unknown alcohol and estimate, given where its E1 elimination is or where the catalytic property is, how its temperature dependence and how its entropy is going to be in such a complex relation. Now let me shift gears. I have shown you in the first part how water changes surface Bronsted acid sites to hydronium ions, and how these hydronium ions change the state of reacting molecules, and how they stabilize or destabilize reaction pathways. Now, what I'm doing now is I'm trying to do the analogous experiments and the analogous deductions for metals in an aqueous or in another solvent environment. We will focus on both. We will focus on the substrate adsorption as well as on the adsorption of hydrogen under those conditions. So those metals react very sensitive, and they undergo reactions themselves, and they stabilize molecules very differently. Let us start with a simple case of hydrogen adsorption on a metal particle. We know that in gas phase, hydrogen adsorbs very stable on, for example, platinum. Theory can follow this up, experiment can follow this up, and we use this to determine how many exposed metal atoms we actually have. When we put this in water, that interaction drastically decreases. It goes from, for a single hydrogen atom, from 36 kilojoules per mole to 25 kilojoules per mole. But not only that, the entropy increases, and the entropy decrease is so much larger in the case of adsorption in liquid phase that we have to analyze this in one of the next slides. So we have both. We have a weakening and we have a larger entropy loss. Can we understand this in terms of a thermodynamic cycle? Again, you see hydrogen binding, 36 kilojoules per mole. You see the dissolution of hydrogen in water, it's not much. You see the 25 kilojoules per mole deadsorption that we have just determined. And we actually need also to consider that we need to remove water which is adsorbed, and that's about 6 kilojoules per mole from platinum into the liquid. So we have an additional contribution on this. But that still leaves us with about 5 kilojoules per mole hydrogen difference compared to the gas phase adsorption. So less stability. Now, this is related to the fact that actually when you are at the metal surface, you get an electrochemical reaction. That means that hydrogen, which is adsorbed, will partly be converted into hydronium ions and electrons on the particles, and it leads to a charge separation at that interface, the Helmholtz plane. But this is not limited to hydrogen. It's actually much larger on different molecules. And here I give you the example of phenol in aqueous phase. Phenol on platinum has about 200 kilojoules per mole adsorption, heat of adsorption. If we try to close the thermodynamic cycle, we see that phenol has to be dissolved in water. That's about 50 kilojoules per mole. We need to remove water from the surface, and that is more water molecules than we had before. So because phenol is larger. And we actually need to consider also the hydration and dehydration of that phenol molecule when it's adsorbed before it goes down to that surface. But taking all this into account, there is a huge difference. Depending with whom you talk, this is around between 80 and 100 kilojoules per mole. This large difference has to be the result of either a very different stabilization of the molecule or a change in the properties of the metal itself. So both will, as I will show you, will play a role, both the stabilization as well as the electronic change in the metal. Let us analyze this. Let us start with the impact of water on the Fermi level of the metal. And I'm talking this here for the case of platinum. Platinum has a difference between the vacuum level and the Fermi level about 5.6 eV. If we submerge it in water, that is reduced to the higher Fermi level that water has, and that leads then to about 4.4 eV. So what happens in terms of orbitals? We see that when we do it in the gas phase, we mix the orbitals of the hydrogen, the adsorbed orbital of adsorbed hydrogen, with those in the platinum. We see we fill the antibonding, we don't fill the bonding orbital. As we increase the Fermi level, we begin to increase the electron density in the metal. The metal is negatively charged, and therefore we are beginning to fill the antibonding orbital, and filling the antibonding orbital then weakens the overall bond between the and weakens the impact of the bonding orbital here. So the enthalpy of adsorption decreases from about 36 to the 25 that we have determined experimentally. There is one more step. If we put a platinum particle in water and we add hydrogen on top of it, this acts as a hydrogen electrode, and we can calculate that potential of that hydrogen electrode, and which is the standard potential of the standard hydrogen electrode plus RT over F, the natural logarithm of the concentration of the activity of protons over the square root of the hydrogen partial pressure. And if we do this, we see that as we are moving from pH 2 to pH 7, as we're decreasing the concentration of hydronium ions, we are decreasing the electrode potential. But we are actually, so we're making it more electron rich, but actually much to our surprise, the hydrogen binding energy moves in the exact opposite direction. It changes from 19 to 23. How can we explain this? It should not be, because the lower pH should lead to a lower of the Fermi level, and therefore to a stronger difference between the bonding and the antibonding orbitals. Now, we can explain this by a property which is related to the outer Helmholtz plane, the arrangement and the separation of charge. In the absence of hydrogen, I have a certain distribution between charge in the outer Helmholtz plane and electrons in the metal focused in there. We know from theory that as we add water, the difference, as we add hydrogen, the difference of this outer Helmholtz plane, the difference of the distance of water increases. And that increase leads to a work. And that work itself has to be subtracted from the bonding of hydrogen. So that works antagonistically to hydrogen adsorption. And therefore, a higher charge density here means more work to be done when we remove it compared to a lower charge density that we're having at a higher pH. So when we take this now and go back and look at the hydrogenation itself, we see that when we hydrogenate an aldehyde function in a series of solvents, we see very clearly this is here on the y-axis the turnover number, so the number of molecules converted per time. So that slope here is the rate, and that rate changes from 3.6 10 to the minus 3 under those conditions to 1.2, so a little bit over 1 order of magnitude. When you look at this, the first question that you may ask is it done by hydrogen addition? So is it a conventional hydrogenation, where hydrogen is a neutral species that is added to either the oxygen or a carbon atom? Or is it by a coupling between a proton addition and an electron addition from the metal? So a proton coupled electron transfer. We know the concentrations at the surface, so we get a little bit an idea of how strong hydrogen is adsorbed and how strong the reactants are adsorbed. Now, the first thing that we want to address is it which of the two pathways does it go? Hydrogen addition, proton addition plus electron transfer. And we see if there would be a proton transfer as a rate determining step, then we should see an isotope effect between water and D2O. We hardly see. But we see a huge effect, independent of whether it's water or D2O, if we switch from hydrogen to deuterium. And therefore, we know in this situation that it must be the addition of a neutral hydrogen to those molecules. Now, the next question is, where is this first hydrogen added to? And we have two possibilities. We can add it directly to the oxygen of the aldehyde. That is called an alkoxy pathway. To the carbon atom of that aldehyde group. That is called an alkoxy pathway because you form an alkoxy group. Or you add it to the oxygen atom. So then it forms an OH group at the surface, and that's why it's called the hydroxy pathway, and there is a carbon metal bond. Now we see again that isotope labeling, where the isotopes go, we can clearly say it is the hydroxy pathway, which is the dominating pathway. Now, let us ask, how does the solvent affect then both the hydrogen addition as well as the activation and the bonding of the reacting molecule? It's a bimolecular reaction, so we need to understand both adsorptions on that surface. And we have measured this independently. So we have measured the adsorption, we have measured the adsorption of hydrogen, and that allows us to construct a complete kinetic reaction sequence out through specific experimental data. We see that in the first part, the amount and the energies of hydrogen adsorbed change, of benzaldehyde adsorbed change quite significantly. But that change is compensated by an equal change in the transition state. So hardly anything that we're doing to benzaldehyde influences really then the transition state. Those are all the same. So the adsorption of benzaldehyde in this particular case does not matter that much. What matters is the adsorption of hydrogen, which is very pronouncedly different. And here you see that this difference really shows back in the difference of the standard free energies, both in the transition state versus in the adsorbed state for the hydrogen. So it is the hydrogen here that dominates and that has a much higher stability in the case of dioxane, and a much lower stability in this particular case of water. And really, this is what you see over that part. You see that dioxane has the lowest standard chemical potential of adsorbed hydrogen, and it has the highest barrier for the hydrogenation. Methanol in reverse, it has the smallest difference in terms of the standard chemical potential of hydrogen adsorbed versus the activity and the delta G standard for the reaction in methanol as a solvent. So solvents not only stabilize reactant molecules, they also stabilize the state of hydrogen. And this is important to consider when designing a reaction. Now we have another way of doing this, and I'm returning back to the situation where we have used localized hydronium ions in order to influence the state and reaction rates. And I will show you that by adding a large concentration of these localized hydronium ions, I'm enabling a switch in the reaction pathway from a hydrogen addition pathway to a proton coupled electron transfer. We show you here an example. We have done this and realized this by placing equal sized platinum particles, smaller than 1 nanometer, in a series of ZSM5 zeolites that have an increasing concentration of hydrated hydronium ions in water. And you see that the transition enthalpy changes drastically when you move from a basically proton-free environment to an environment where you do have a lot of hydronium ions. You see that that rate increases almost tenfold, and the activation energy is significantly lower. So now let us check for a second whether we really change that mechanism. And we can do this, we turn again to isotope labeling. We use deuterium in order to show that, because we know that if you have a proton coupled electron transfer, the ortho and the para position are preferred and probably equally populated, while in the other case, when we have a hydrogen added, we tend to have this close to the O'Day group. And we clearly see that the hydrogen addition dominates in platinum on silicalite, where no hydronium ions are in, or very few hydronium ions are in, and it is completely statistical. And when we have a large concentration of hydronium ions, so we can use labeling to show in which direction we can drive that reaction. And the question comes, can I induce that? Is this a peculiarity of the zeolite, or can this be done more general by changing hydronium ion concentration? That's why we turned to platinum on carbon nanotubes, and we change from pH 2 to pH 5.5. And we clearly see at pH 2, there is no impact whether I'm using hydrogen or deuterium in order to run the reaction. But there is a huge impact between deuterium oxide and water. So this is a situation where a proton coupled electron transfer dominates. Here at pH 5.5, it's just the opposite. There is hardly a difference between water and heavy water, but there is a huge difference between hydrogen and deuterium. So we see that in this case, we are dominated by a hydrogen addition type mechanism. And as I've shown you before, the proton-coupled electron transfer has the lower activation energy, and therefore the turnover frequency really increases with pH, both being on a log scale. So having shown how much we can influence by changing the local environment, changing the charge, changing the hydronium ion concentration, and changing the solvent, let me turn at the end of this lecture to the additional factor of an external electric potential and its influence on reaction rates and pathways. We start again with the absorption of water, hydrogen in aqueous phase. So we have the enthalpy of adsorption as a function of the positive overpotential. And see, with the positive overpotential, the interaction strength increases. And as I've shown you before, with this holds for each of the pHs. So the separation of the Helmholtz layer and the surface is independent of that overpotential. But of course, you note that it is the same. It's the same sequence. A lower proton concentration in the electrolyte leads you to a better stabilization of hydrogen. Same story, explained through the orbitals. A higher positive bias will change change the Fermi level, and that change in Fermi level will stabilize hydrogen bonding. We can turn then to a cathode, and we can change here on the cathode the negative potential that we have. And we see that with increasing negative potential, we increasing hydrogenation rate. We see that we make it not only through that negative potential more favorable to hydrogenate, we also the negative potential makes sure that there is more hydrogen available at that surface. The difference between the individual metal changes the relative selectivity between hydrogen addition to the organic substrate and hydrogen recombination as hydrogen evolution reaction in this case. And you see clearly that for rhodium, it is quite easy to recombine. For palladium, that interaction is stronger, it's more difficult, so hydrogenation is more favored, at least hydrogenation of an aldehyde is more favored under those conditions. We can go one more step. We can actually set the chemical potential of the metal by changing the hydrogen pressure. So we go here from 0.1 bar to 1 bar. That changes the open circuit potential and the open circuit voltage as a consequence in this case. And we see that it doesn't matter as long as it's equivalent, the hydrogen pressure or the absence of hydrogen and the external potential that I'm doing, that I'm applying, has the same effect on the rate. So in both cases, both for 0.1 bar as well as for 1 bar, the rates between an electrochemical hydrogenation and the addition of hydrogen is identical as long as I have the equivalent of the same hydrogen chemical potential and or the same electric potential from the outside. That means for us, thermal chemical hydrogenation, the addition of hydrogen, and electrochemical hydrogenation share the same reaction rates and the same reaction mechanisms. So we have to deal with this in the same context, and therefore we will investigate whether a local charge will shift, and local hydronium ion concentrations will shift again the mechanism. We see that at a surface of a carbon support with a particular size of metals, always the same size of palladium, those are approximately 2 nanometer palladium particles, 3 nanometer palladium particles, but constant size. We see that with increasing concentration of acidic groups, those were induced by treatment in ozone, these acidic groups enhance the reaction rate. Why do they this? They provide locally protons, and they allow locally a hydrogenation through an electron, through a proton-coupled electron transfer, and through an easier path for this hydrogenation. And that gives us the opportunity really to promote specifically reduction reactions and to focus on the design of a specific transfer into functional groups. This is only the beginning that we're seeing, but electrocatalysis and organic electrocatalysis will help us fine-tuning some of the hydrogenation reactions. That brings me to the end of this presentation. I have tried to show you how to manipulate the ground state and how the impact of water, pH, and that environment helps us to elevate that state to a higher level, and therefore to minimize the barrier to convert molecules. We have also shown you how the measures that we can take to lower that transition state, the steric possibilities, as well as the stabilization of a charged transition state in a charged environment. And all together, that gives us the opportunity to direct catalyzed reactions at an unprecedented level. But I also wanted to convince you that water as a solvent, and many of the protic solvents, really change active sites, they change the electronic properties of the catalysts, and they change excess potentials of their reactive substances that are being converted. This is not an additive process. This is really a chemical reaction that takes place. I've shown you specific examples how this works with hydrated hydronium ions that are entities and were in a small nanoreactor in which the organic molecules can be converted and in which their ground state and their transition state is being modified by the ionic strength. I've shown you how metal catalysts undergo electrochemical reactions that change their surface properties and open new reaction pathway. And I have shown you at the end that we can additionally take electric potentials and shift that change and shift that chemical state of the metal even further and add another layer of excess potentials to drive chemical reactions and to change rates of reactions along a particular pathway. I would like to end by thanking a really large group of people and two fantastic teams that have grown together over the last years and have discussed in a way that was exciting to watch. The team on the left side in Munich, the team on the right side at PNNL. I have really had a privilege to work with a wonderful set of people. We had a wonderful set of senior visitors that we had long-time collaborations. And among those, I would like to highlight Gary Haller and Charlie Campbell. I would like to highlight also a group of senior people that I had the pleasure to work with that helped in that sometimes difficult process of educating all of us together. And I'm grateful for the continued trust of the sponsors, ranging from the Department of Energy, and particular basic energy science, of the DFG, the BMBF in Germany, the European Union, and industry, as well as the 2 locations which gave me the privilege to work both at TU Munich and at Pacific Northwest National Laboratory. And I would like to thank you for sharing the time, and I'd be happy to answer questions by email or whatever form the organizers will set. Thank you.